All right, folks, it's Miss Stryker here. I wanted to do a very quick reminder video or a first-time overview of the parallel plate capacitor, since one of our problems, I think it's problem 4 this week, has to do with a parallel plate capacitor. So I've drawn here a parallel plate capacitor, and I have charged up the top plate positively and the bottom plate negatively, and those plates are separated by a distance d. Now, d is usually a very small number. It's much smaller than a millimeter. Okay, so those parallel plates are actually very close together. And I wrote down some definitions over here. So my first definition is that the electric field is defined as the force per unit of charge. Potential energy, which sometimes is known as PE and sometimes is known as U, is the opposite of the work done by the conservative force. I'll talk about that in a minute. The opposite of the work done by the conservative force. And then that the potential, this V here means potential, is the potential energy per unit of charge. And that's known as electrical potential. So you can probably see that it's easy to mix up potential and potential energy. But we will talk about both. Okay, so D is really small. And here's my parallel plate capacitor charged, let's say, to a potential of, it doesn't really matter what my potential is. There's some potential difference there. If I've attached it to a battery, maybe it's 1.5 volts. Okay, so let's talk about what's happening inside that parallel plate capacitor. So I know that the electric field goes from positive to negative, and that the parallel plate capacitor is one of the only places where the electric field is going to be consistent or uniform. So I'm trying to make my lines evenly spread here, and at the edges it kind of bends out a little bit. Over here it kind of bends out a little bit, but it is a uniform electric field, and so I'll just put E in there. Now, if I imagine putting a little positive test charge or a positive charge inside that parallel plate capacitor, you know that it would be stuck to the negative plate. Opposites attract. And it doesn't want to be anywhere near the positive plate. It's stuck to the negative plate. So it's very happy there at that negative plate. If I were to force it up to the top plate, it would become very uncomfortable. And that really is an increase in that charge's potential energy. The more uncomfortable it feels, the more potential energy it has. It's just like lifting something up in the gravitational field. The higher you lift it, you can imagine the more uncomfortable you would feel, because as soon as you drop to the ground, right? You naturally move in a way that reduces your potential energy. And that's because the electric field pushes it down. And so if I were to move this up to the very top, how much work would I have to do? The work that would be done by me in pushing that up, well, we know that work is force times distance, basically F times D times the cosine of the angle, but I'm going to be pushing it straight up, right? A distance D. And what do I have to oppose in order to lift it? Well, I have to oppose the electromagnetic force. And I know I can write that as E times Q, the amount of charge that is contained on that little positive charge. So E times Q times D is the work that's done by me. What about the work that's done by the electric field? Well, the electric field is pointing down, but my displacement is pointing up. And so the work that's done by the electric field would be negative E times Q times D. All right, same size, just different sign. Regardless, that charge now has a potential energy. Energy of the charge, and it is E times Q times D. That is the potential energy of the charge. Notice that it is the opposite of the work done by the conservative force, or by that field. Okay, so E times Q times D. So I'm just going to simplify this as U, potential energy, is E times Q times D for charge Q in uniform E field moved a distance D. All right, so there is my potential energy. So now I can figure out what is the potential, the electrical potential. And by the way, let me go back here for a minute. We know that potential energy measures in joules. And so my electrical potential is going to be the potential energy per unit of charge. And so if I just divide my formula by Q, I get E times D. And that would measure in joules per coulomb. Or we commonly call that a volt. So you can call that a joule per coulomb or a volt. And that is how the electric field in between the two parallel plates that are separated by a distance d relates to the voltage. And you would apply the voltage via a battery, and then depending on the separation between your plates, you would adjust the electric field. All right? And so parallel plate capacitors are very, very common. And you have one problem that has to do with a parallel plate capacitor. Imagine putting a negative charge inside of that electric field. I know that the negative charge would be not pushed down, but it would be pushed up by that electric field. So your problem coming up in your packet this week has to do with a negative charge, not a positive charge. And maybe the plates are oriented a little bit differently. You'll have to read that carefully. But this is what's happening with the potential energy and the potential, the electric field, and the distance between the plates for a parallel plate capacitor.